we have studied order of element divides order of group.
Yeah, order of the elements divides the order of the group, correct?
Then we can directly say that order of x cannot be 2.
Order of x cannot be equal to 2 because it doesn't divide the order of G. Therefore, it has to be 1. Therefore, kernel is 1. Okay.
Yes.
Fine. Okay.
And question 16.
Yeah. Okay, so what is question 16? Let me just see. Question 16. So, okay, so K is a subgroup of H is a subgroup of G. So if it is finite group, then it is not difficult to show, right? I have asked for finite groups. For finite groups, still you are not able to do?
No, ma'am.
No? Anybody have done for
G is to
finite
H
group?
equal to order G by order
No,
H. From that, we can say.
Yeah. Correct. So let me see. This is question number, what you said? 16 or 17?
16, ma'am.
16. Okay. You have, I think H is a subgroup of, what was this chain of subgroups?
K is subgroup of H. H is subgroup of G.
Okay, this was the chain. And then what is this G colon K?
Equals to G colon H multiply H
Yeah.
colon.
Yeah. So what do you already know? How do you find the index? What is
Order
the
of G.
index of a subgroup? Order of G divided by order of K, isn't it?
Yes, ma'am.
Now I need to prove it, like I need to relate it with this other things. So what is your G colon H into H colon K? So this is order of G divided by order of H. And what is H colon K? Order of H divided by order of K. So this is nothing but order of G divided by order of H.
We can prove like this.
Yeah, if the this group is a finite order, then you can prove in this way.
Ma'am, I thought I tried using theoretical proof, not this.
No, this only. But now the thing is that if order of G is infinite, then still it is true. Then how to prove? Somebody have tried how to proceed in this case?
Ma'am, I tried, but I don't know is it true or not. Would I say?
Okay, let me explain first, because it is little bit difficult here. If sometimes, so can you briefly say the idea, what you have tried to apply? Then maybe it will be easier. So what you have tried to do
Ma'am,
here?
first I find the partition of H by H intersection K, as H intersection K is a subgroup of um, mm, H. Then as every coset of every coset of H intersection K is equivalent. That means there is a bijective correspondence between every cosets of H intersection K. So then I tried that
bijective correspondence between which sets?
H intersection K to every coset. That means A H intersection K for every A belongs to. That means distinct left cosets of H intersection K.
With Distinct left cosets of H intersection K is in bijective correspondence with what?
H intersection K. That means elements of, if I take two sets,
Yeah,
A,
the now cardinality of a left coset is same as the cardinality of the subgroup. That is true.
I applied this. mm, Then I find that H intersection number of distinct left cosets of H intersection K are multiple of um, index of G index of H in G.
Index of H in G. You are saying that, okay. Okay, whatever the idea you are telling, that might be same what I'm trying to say, but it is difficult from here to understand. So let me just describe what I'm trying to say, then it will be maybe clear.
Using third isomorphism theorem, we can do.
Yeah, using that also you can do. Using that also you can do. There is not a unique way of doing it. So there are many ways. So what I will, just let me say one of the way. So H is a, you have this K subgroup of H subgroup of G. Okay. So now what do you know? That G you can write as disjoint left cosets of H, right? Say this is over some I equal to 1 to n. Since the index is finite, so G can be written as disjoint union of the left cosets of H. Okay. And similarly, I can write down my H as disjoint union of left cosets of K. Correct? Isn't it? So then what I can say from here, that this G, which is disjoint union of the left cosets of H, now this H can be written as disjoint union of left cosets of K. So this one I can write it as nothing but union of GI of union of HJK. Isn't it? Correct? So what finally I'm doing, that it is nothing but disjoint union of, say, GI HJK, where I and J are varying over the indices. Okay. So now I have written that G is the this union of GI HJK. I have written it. Now what will be enough to show? If I am able to show that any two sets here GI HJK are disjoint, then it will be done.
Ma'am, could you repeat previous thing, that G equal to union of GIH?
So G equal to union of GIH. This is because I am considering that this G colon H is finite. There will be finitely many left cosets. So I will be able to write down G as disjoint union of the left cosets of H, say M. And then this H is again disjoint union of left cosets of K, because this index is also finite. Is this okay?
Yes, ma'am.
Then I have just written down this H as disjoint union of the left cosets of K. Then finally what I am writing? I am writing G as union of this left cosets of GIHK of K. But then I have to show that if all of them are distinct, all of these left cosets are distinct, okay, are disjoint, then what we will get? We will get that the number of left cosets of G colon K is nothing but M into N, isn't it?
Yes, ma'am.
So we need to, it is enough to show that these are disjoint. Okay. So in order to show that these are disjoint, what we have already? We have already that the left cosets of H are disjoint, right? So GIH intersection GTH is empty because the left cosets of H are disjoint. Okay. Now if I from this I can write it that GI of HJK intersection GT of HSK will also be empty. If these two are empty sets, then this H is disjoint union of this left cosets of K. So if I just take one of the left cosets, then this will also be empty, isn't it?
Yes.
Okay. Now this is true when I am taking this GI and GT are different. Okay. But it may happen that this I can be equal to T, but this J is not equal to S. In that case also I have to show they are disjoint. It covers the cases here when I and T are different. In that case, I am able to show that these are empty. But if I is equal to T, in that case also I have to show these are empty. Now we will use the fact that the left cosets of K are disjoint. So since HJK intersection HSK is empty, so I can say from here that GIHJK intersection GIHSK is also empty. Therefore, it is done. Is it fine?
No, ma'am. Did not get that thing.
Which one?
Where
Okay,
we
first tell me is if we are able to prove this, then is this thing clear? If you
no, ma'am.
assume that this is empty, that is also not clear. What I have shown here, G is disjoint union of the left cosets of H. Okay, so I have written first this G as disjoint union of this H, but then this H is again disjoint union of this left cosets of K. Correct. So then if I further write H as disjoint union of left cosets of K, then I can cover my G with the elements of the form GIHJK, which are left cosets of K, where GIHJ is varying over all the indices of I and J. So these are elements of G. Is it fine?
Yes, ma'am.
So now if we are able to show that all these left cosets are disjoint, then what will be the number of left cosets here? I is varying from 1 to n, j is varying from 1 to m. Then if all these things are disjoint, then how many left cosets will be there?
There M into N.
M into n. So in that case, I will be able to prove that G colon K is M into n, isn't it?
Yes, ma'am.
So that means it is enough to show that all these say left cosets are disjoint. That means their intersection is empty. That is what we will try to prove now. Is this fine?
Yes, ma'am.
So here we have proved the fact. So what we have done, we know that the left cosets of H, these are the disjoint left cosets of H. So if I is not equal to T, then this is empty, I know. Okay. Now this H is nothing but disjoint union of HJK. So instead of all, oh, this is, if I take one piece, then of course this intersection will also be empty, isn't it? This H is covered by this type of sets. So I have just picked up any one of them. So that even will be even smaller than this one, no? So if this intersection is empty, then definitely this intersection will be empty. Is it okay?
Yes, ma'am.
Right. But here, what is the problem I am facing? That this covers all the cases, but then I is not equal to T. But I can be equal to T because here I am varying I and J both. So I can fix my I and vary my J. In that case also I have to show they are disjoint. So that's why I have now taken that the left cosets of K are disjoint. Now I am taking that, okay, HI, HJK, if a GI I am now multiplying with the same thing, then they are also disjoint. Okay.
Yes, ma'am.
Ma'am,
Thank you.
in the
for-
third last line, shouldn't it be GI intersection GTHJ instead of S?
In the which line you said?
Third last line. For all I not
This
equal to
one,
T.
this
Yes,
one.
ma'am.
Yes.
HSK, because we are substituting H as one of the HJK.
HSK. Yeah. So I'm considering any of this H is here. H is can be written as here. So I'm taking any piece from here. That I'm denoting by HSK. Did I answer your question, or I didn't understand your question?
Ma'am, why is it HJK? I didn't get that part. GI HJK intersection GTHS.
Why this is empty? That is what you didn't follow?
Yes, ma'am.
Okay, so I'm saying that this GI of H and GT of H are disjoint. Okay, now H is disjoint union of these left cosets. So I am taking one piece, say HJK from here. Right. So this will be sitting inside this one, no?
Okay, ma'am. Okay, ma'am. Got it.
Okay. Yeah. So now is it clear to everybody? Even if it is not finite, the order of the group is not finite, then also we can, this is still true. Okay. There might be other proofs
Ma'am,
also. Yeah.
ma'am, can we show that if they are not equal, then they would be disjoint? Like either the two cosets are equal or disjoint.
Equal or disjoint. Yes. Right. Yes. Yeah. So any other, yeah. What is the next question now?
Ma'am, in question number 11, we find all order of all the elements. Then how we show that this is isomorphic, like through a definition of D4, D4.
Yeah, so the definition of D4. So what is D4? You know that D4 is generated by two elements. One is of order 4
Two
and
and two.
another one is of order 2, right?
Yes.
And they satisfy certain relation between them. Correct?
Yes,
They
ma'am.
satisfy certain relation between them. Okay, so now whenever you are trying to show that this group is isomorphic with D4, then what you have to do, you have to show that this group can also be generated by two elements. One of them is of order 4, another one is of order 2. Okay, and then you define the map such that order 4 elements goes to the order 4 elements of D4, and order 2 elements is mapped to the order 2 elements of D4, and this relation in whatever is satisfied in D4 is also satisfied in this group. Then it will be an isomorphism. Is this clear what I have told? If not, then tell me. I will try to do it.
Ma'am, here it's the dihedral group of order 8.
Yes.
So I just
Yes.
wanted to know how exactly is the dihedral group formed by those symmetries of octagon or something like that?
The symmetries of a square.
That is for
Symmetry.
order 4, no, ma'am. If it is order
No,
8,
no.
we should. Okay.
No. Oh, see, what are the symmetries of a square? How many symmetries you have?
4 reflection, 4 rotation.
So how many elements are there?
8 elements.
8.
8 elements are there, right? So
Yes,
D4 is nothing but the dihedral group of order 8.
yes, ma'am. No, I was asking for D8, not D4. If it is like D8, then.
If it is
Okay.
D8, then okay, maybe I have not described the general form of a dihedral group. No.
Yes, ma'am.
So yeah. So let me just tell it here. What is the general form of a dihedral group? So again, you have like a regular, maybe I will just say a dihedral group is the group of symmetries of a regular n-gon including both rotations and reflections. Okay, so basically a regular polygon with n sides has 2n different symmetries. N rotational symmetries and n reflection symmetries. Okay, so now if you consider say Dn, so the cardinality of Dn is basically 2n, where n number of rotations are there and n number of reflection is there. It is generated by two elements x and y, where x is a rotation by 2 pi by n degree. So x is of order n, and y is a reflection. So y is of order 2, and the relation between x and y is yx is equal to x inverse of y. So this is in general. So the elements of this group, if you see, are nothing but there are two n number of elements, 1 x, x square, so on up to x minus 1. These are all the rotations, and then you are having reflections y, x, y, x square y, so on up to x to the power n minus 1 y. Okay. So this is the dihedral group of order n. Okay, I think in Damitton foot the notation is little bit different. The dihedral group of order 2n, they are denoting it by D2n, but in Artin the notation is Dn, order of Dn is equal to 2n. Is it now okay? Those someone who was asking about the dihedral group, what will be
Yes,
the
ma'am.
general form? Okay. Yes.
Converse of Lagrange term is true for dihedral group.
Converse of
Lagrange theorem.
Converse of Lagrange theorem is true for dihedral group.
And
I have to check. I will not be able to answer. Okay. Yeah. Okay. So what is the next question?
Question number 15.
Question number 15. Okay. So question number 15, we will use this question number 16 in some case, and then we will try to do. Okay, so G colon H is M, G colon K is N. Then you have to prove this. Anybody has done question number 15? Anybody? So we would like to see the relation. So I think LCM of Mn is less than equal to what was that relation? Can somebody tell me?
G colon H intersection K
G colon H intersection K
less than Mn,
Mn. Okay.
where M is G
So
colon H and N is G colon K.
yeah. Okay. So let this G colon H intersection K is equal to L. This number is L. So what I am having? I have this G, then I have this subgroup H, and then I have another subgroup K, and then I have this subgroup H intersection K here. Okay. So from here, what I can say? I can say that this G colon H intersection K, this H intersection K is a subgroup of H as well as it is a subgroup of K, isn't it? So now if I consider this chain of subgroups, then this, by the next exercise we see that this is nothing but G colon H into H colon H intersection K. Correct?
Yes, ma'am.
Yes, ma'am.
And this is also same as, now instead of this one, if I use this chain of subgroups, then I can write this as G colon K into K colon H intersection K. Okay, this is the same thing, right? So basically what I am getting, so this is equal to L, I have assumed. So I am getting that L is equal to M times some P1 and L is equal to also N times some P2. So then from here, can you say at least get the lower inequality? Are you getting the lower bound from this?
Yes, ma'am.
Yes,
So
ma'am.
say M
LCM.
divides and L and N divides
N
L
divides L, so
and M.
LCM should be less than equal to L, right? So from here I can write that LCM of M comma N is less than equal to G colon H intersection K. We need to only show now the upper bound. Okay, for the upper bound, I'm giving you this is as a small exercise. You try to show. If you are not getting, then maybe tomorrow I will do in the class. exercise is to show that H colon H intersection K is less than equal to G colon K. Okay. If you use this exercise, then can you get the upper bound?
Ma'am, this is basically P1 is less than equal to N.
Yes.
Yes, ma'am.
Yes.
Then we can directly say
Then
L
you
is less.
can, yes, Mn, right? So only thing now you have to show that the left cosets of H, number of left cosets in of H intersection K in H is same as is less than equal to number of left cosets of K in G. Okay. So these are, you little bit think, if you are not getting, I will tell you tomorrow, but just give a thought about it. Okay. Yeah. So next. Is there any other question?
Question number 20.
Question number 20. Okay. Let P be a prime number, N be a positive integer. Find the order of P bar n z quotient P to the power n minus 1 z cross and deduce that n divides this. So which part? Both the parts or any
Both.
one of them? Both. Okay. Anybody tried this question number 20?
Yes, ma'am.
Yeah. So how you have done question number 20?
I consider the group of order U. I consider the group U Pn minus 1. That means Z slash Pn minus 1 Z upper A cross, and that means the multiplication group.
You are considering all the non-zero elements of this z quotient P to the power n minus 1n, all not
No,
that
no,
all
ma'am.
the elements which are co-prime to this.
Co-prime to Pn minus 1.
Okay. Then
Its order is I Pn minus 1. Euler's 500. Now I want to show that if that means P to the order of P is n, I would show it if I take no, P power m congruent to 1 mod Pn minus 1, then I find that P power m minus 1 equals to K into P power n minus 1.
okay, so let's go slowly. So see, you are considering the group G to be this group. What is this group? This group is nothing but the collection of all the elements of the form A bar such that GCD of A and P to the power n minus 1 is equal to 1, right?
Yes, ma'am.
This is the group you are considering, right? And we have seen that this is a group with respect to multiplication.
Yes, ma'am.
Congruence multiplication. Okay. So now you are trying to find the order of P bar here, right?
Yes, ma'am.
So for that, what you have to show first?
I have to show first that P power n congruent to 1 mod P power n minus 1. And
so P bar to the power n is equal to 1 bar in this group, isn't it?
yes, ma'am.
In this group G, P bar to the power n is equal to 1 bar, right?
Yes, ma'am.
Is it clear to everybody that p bar to the power n is equal to 1 in G bar in G? The person who have asked the question?
Definition
No?
of G is not clear by A bar. GCD
Can
of
you
A.
okay, so why okay, how, what is this that is not clear to you? Why, how this is forming a group?
Yes, ma'am. Yes, ma'am.
Let's
How this is?
okay, so
How
let's
is
take one example, maybe it will be a little bit better. So let us just
yes.
consider Z quotient 10Z. Okay, forget about p to the power n minus 1 and all. Just consider the this group Z quotient 10Z cross. What is that? So this is the elements A bar such that GCD of A and 10 is 1. Okay. So now what are the elements here? Can you tell me? 1 bar
1379.
3, 7, 9. Correct. Yeah. So now with respect to multiplication, this forms a group.
Yes, ma'am.
Yes.
So this forms a group with respect to multiplication. Fine. So whenever you have this Z quotient NZ, then this is always a group with respect to multiplication. This I have told while I was doing this, giving examples. Okay. So now here we have considered p to the power n minus 1. This. Okay. So in this example, Z quotient 10Z, what is this? If you consider here, so what is, for example, in this, your Z 10 bar is equal to 0, isn't it? In this here, this 10 bar equal to 0 bar, right here, isn't it?
Yes, ma'am.
So that means what you are getting? You are getting that 9 bar is nothing but. So similarly here, so from here I can say that in this quotient, in this group also, p to the power n minus 1 is 0. Right? That means p to the power n is congruent to 1 modulo p to the power n minus 1. That means in this group, I am getting that p bar to the power n is equal to identity. Is it clear?
Yes, ma'am.
So that's what I have shown here, that if I raise p bar to the power n, then I am getting identity element. Okay. But now I have to show that order of p bar is actually equal to n. That means n is the smallest positive integer such that if I raise it to n, then I will get identity. Isn't it?
Yes, ma'am.
So for that, yes.
Ma'am, we define in the last line where you've written Z, Z mod and Z cross.
Yeah.
This is defined to be A bar such that GCD of A comma N
Yes.
is equal to 1.
1. Yes.
Okay. Okay.
This is the notation. Okay. This is the notation. Sometimes
Okay.
they use also this to be nothing but units of Z quotient NZ. Units means if you look into this, then all these elements have multiplicative inverse. those which are co-prime to n, they are having multiplicative inverse. That's why they are forming a group with respect to multiplication. So in some sense, these are calling units of z quotient nz also. Okay, somebody use this notation. So now if I want to show here that I have shown that p bar to the power n is giving me identity, but I want to prove that n is the smallest positive power which is giving you this identity, then order of p bar will be equal to n, right? So suppose that there exists some element which is smaller than n such that p bar to the power that integer is giving you identity. Okay. So wants to show that order of p bar is equal to n. So let k is less than n such that p bar to the power k is identity. But if p bar to the power k is identity, then what will happen?
K will divide, n will divide k.
Then in this group, z quotient p to the power n minus 1, in this group, this p to the power the numbers which are between p to the power k and p to the power n will also be zeros, and then this cardinality will not be same, right? You understand? If p bar to the power k is equal to 1, then this is where in this group p to the power n bar is identity, not some less power is identity. Okay. Is this clear to you or not?
Ma'am, so here we can say that order of p bar divides n. First we proved that, but now we have to prove that order of p bar is actually equal to n.
Yes, right.
Right.
That
So
means you
for
have
that,
to prove, yeah.
so for that, you just took k as the let k be the order of p bar, and you raised it to the power k and you equated to 1, right? Now, what is your argument that only p power n should be equal to 1? I didn't get that part.
Yeah, so what from here, if p bar to the power k is equal to 1, then what I am getting? In that case, I am having that p to the power k is strictly less than p to the power n minus 1, right? Isn't it? If k is less than n, in that case, what I am getting? That p to the power k is strictly less than p to the power n minus 1, isn't it?
Yes, ma'am.
But in this group, I'm in this group, no? In this group, is it possible that some lower power of p will in this group, what I am having? In this group, I am having that p to the power n minus 1 is equal to 0, isn't it? Some lower power of p will not give you this thing. I'm not able to express, maybe. Is it clear? Means in this group.
Ma'am.
Yes.
Ma'am, I used that if p power k order of p bar is k, then I have p power p bar power k equals to 1. That means by using a congruent operation, I can say that p power k minus 1 equals to some constant into p power n minus 1.
P power k minus 1 is equal to some constant into p to the power n minus 1. Yeah, that is better in that way. Yeah.
That means p power n minus 1 divides p power m minus 1. Uh, so p power n minus 1 must be less or equals to p power.
Okay. Yeah, I understood. Now, okay, now it is much better in this way. Maybe, so say, if p bar to the power k is equal to 1, then what does that mean? It is in this group it is happening, right? That means that p to the power k minus 1 is L into p to the power n minus 1, isn't it? But is it possible for any value of k which is strictly less than n?
No, ma'am.
Now, is it clear? The student who asked me at the end this argument, how it is coming?
Yes, ma'am. Yes, ma'am. It's clear.
Okay. Yeah. So that's why n is the smallest possibility. So therefore, order of p bar is equal to n. Fine.
And order of this entire group is phi of p power n minus 1.
Exactly.
So n divides that.
Exactly.
Yes, ma'am.
Okay. This order of this is nothing but phi of p to the power n minus 1. Okay. And order of p bar is equal to n. This implies that n divides phi of p to the power n minus 1. Okay. Okay, I think the time is up. Is there any other question left?
Then can you repeat last things? I did not get that. How you proved that the order exactly equal to n, order of p exactly equal to n.
Okay. So what I have said that suppose there is, so if I am able to show that suppose n is not the order, that means there exists some integer less than n such that p bar to the power k should be equal to 1, which is the order.
Yes, ma'am.
Okay, but p bar to the power k is equal to 1 bar. This is happening in this congruence modulo p to the power n minus 1. That means what? That means that p to the power n minus 1 divides p to the power k minus 1.
Yes, ma'am.
But is it possible that this k is less than n and still you are having this relation holds? This is not true, right?
Yes, ma'am.
So therefore it has to be n only. You cannot take anything smaller than this. Okay. Yeah. Okay. So is there any other questions left in this exercise? In this tutorial sheet?
Yes, ma'am.
Which one?
Ma'am, question number 7. Actually, I did not.
7. Okay, fine. So maybe 7, and I think Z and S3 I have discussed. Only Z quotient NZ is left. So maybe tomorrow I will first in 5 minutes discuss that and then I will proceed for the lecture. Okay. Any other questions? No. Okay. Or you can discuss among yourselves also. Those who have already done some of the problems, you can take help from your friends and discuss with your friends. And then if some problems is still not, you are not able to solve or understand, then you can ask me those problems. Okay. Anyway, that question I will discuss tomorrow first and then I will start the lecture. Okay.
Ma'am, excuse me, ma'am.
Yes.